Hello everybody. Today we're going to do something a little bit more sophisticated. Do you remember me talking to you about the differences between the deterministic and stochastic approach in scheduling? Deterministic is one thing, less complex, much convenient, we do use it, but the stochastic approach is probably telling us more about the truth and what is really happening out there. And this is why today we'll be talking about the program evaluation and review technique, or as everybody calls it, PERT. You will find out that PERT will let us answer some questions which are really very important for the project manager, like what is the probability of finishing the project at that much time. So first of all, let's have a look on which are the steps that we need to do in order to calculate through PERT the scheduling of our project. The first thing is to define A and B durations. In a minute, I will explain what these durations are. Then we're going to calculate the mu and sigma values at the activity level, which is the mean value and the standard deviation for an activity as far as the duration is regarded. Then solve the CPM network, nothing new here, as we know to do it, and then calculate the mu and sigma values for the project level. If we have this information, we will come up with a distribution, with a normal distribution that will describe the duration of our projects. And then, with a little bit of statistics, we will be able to calculate the probabilities. Let's see how we take these steps. So let's come back to our nice small construction example. The activities, framing, drying, utilities, second fix, glazing, inspection, and so on. We have the predecessor, we have the durations. And this is a deterministic word. So in the deterministic word, we can have one single duration for each activity. But this is not always the case. And that's why we need to define A, M, and B. What is A, M, and B? So A is the optimistic duration, the soonest that we can, or in the past we have completed the activity. M is the most probable, which is what usually happens, while B is the pessimistic, which is the longest that once this activity has taken. As you see now, I have used the deterministic durations as the most probable ones. Why? Because most of the times this is the case. When we do deterministic scheduling, we use the most probable durations as the duration of the activities. So A is for optimistic, M is for most probable, B is for pessimistic, and this is a convention that is used in PERT. So you will always, or most of the times, be seeing these letters to stand for optimistic, most probable, and pessimistic durations. Obviously, the optimistic duration is going to be less than the most probable, and the pessimistic is going to be higher than the most probable. I need to say here that there is an underlying assumption in PERT, and this underlying assumption is that the duration of every activity in the network follows what we call a beta distribution. But at this stage, I don't believe that you need to know anything more than that. Okay, so we have defined A, M, and B. What's next? The next thing is that for each activity, we have to calculate the mu value and the sigma value. Mu stands for mean duration. And our French mathematicians and statisticians, they have came up with a formula that tell us that if we have a beta distribution, we can have a very good approximation of the mu, of the mean value, if we apply the formula that you see on the screen, which is A plus 4 times M plus B on all of that over 6. That's quite simple mathematics to do. So let's take an example. For activity A, you will have 2 as the optimistic value, 4 as the most probable value, and 12 as the pessimistic value. So it's 2 plus 4 times 4 plus 12, and all of that over 6, which makes 5. If you calculate the mu of all the durations of its activity, of all durations of the network, you will come up with the total mu values. So you have A5, B7, C5, and so on, using the formula that you see on screen. As simple as that. This is simple mathematics. The next thing that you need to do is to calculate the sigma. And again, our French mathematicians, they have came up with another formula, which says that if you want to get the standard deviation, the sigma value, you have to do B minus A over 6. Now, it's interesting for us to be reminded of what the standard deviation is. So assume that you have a curve, and you have a sigma value in one case, which is, say, 1, and in another case, you have a sigma value which is 2. The sigma value, the standard deviation, will practically tell you how open the curve is. So whether the values are concentrated next to the mean, this is small sigma values, or they are scattered away from the mean. This is bigger sigma values. So that's the natural meaning of a standard deviation, in very simple terms, of course. Let's do an example for the sigma value. So for activity A, the pessimistic duration B is 12, the optimistic is A. So you have 12 minus 2 on the numerator and 6 on the denominator, which makes roughly 1.67. And you can do the same for all the other activities. And if you do that, you see that all the other activities share the same standard deviation, despite that the numbers are a little bit different. The product of the outcome of the deviation is 1.33. So now we practically have a new table. This new table is offering us more information, and what's that information? It's the mu values and sigma values for all the activities. The next thing that we need to do is to concentrate on the mean values, and now we'll be doing something that we know, is to solve the CPM network. But this time, instead of solving the network with most probable values for the durations of the activities, we're gonna use the mean values. Remember, when you solve the network, after constructing a network, the first thing that you should do is to put the duration of the activities on the network. That's an easy thing. Remember, when you're doing PERT, these are the mean values of the activities. And then you do the forward pass. Remember, when you do the forward pass and you have merging activities, like for instance D in this network, you take the maximum of the early finish of the predecessors. So in this case, D has B and C as predecessors. B has an early finish of 12 and C has an early finish of 10. So the maximum of these two values is 12. And you keep moving from the left to the right and calculating early start and early finish values for each activity. So this is the forward pass. And now you came up with a duration of 18 weeks. This duration, as you can see, comparing to the CPM network that we have solved with the deterministic approach, where we use the most probable durations as the durations of the activities on the network, it indicates that the project is going to take longer to finish. And that's rational if you think about it, because as you saw, the pessimistic duration for each activity was a little bit more far away from the mean value than the optimistic activity was. So we do have the forward pass now, and the next thing is to make the late finish of the finishing node equal to the early finish of the finishing node, and then we can start the backward pass, moving from right to left. And here, remember that the trick is with the bursting activities. So if, for instance, you go to activity A, which is a bursting activity because it has two successors, more than one is a bursting activity, you will have to pick for the late finish of activity A the minimum between the late start of activity B and the late start of activity C, which is pick between 5 and 7. And you take the minimum because you are on the backward pass, so the late finish of activity A would be 5 weeks. And now you have completed the network. You have the CPM, and of course you can do the critical path. This critical path might be the same as the one that we found when we did the deterministic approach, but pay attention to the fact that when you do PERT, and instead of using the most probable values for the duration of the activities, you use the mean values, it is not necessary that the critical path will remain the same. So you may find that the critical path may change. All right, we've done that. What's next? The next thing is to calculate the mean value of the project. So the whole PERT thing is based on something which is called the central limit theory. And the central limit theorem will tell us that when we add variables which are described by the beta distribution, in this case we are adding durations described by a beta distribution, the outcome will be a normal distribution. This is not very deep statistics, and you can find plenty of information about how this works. But the point here is that what we're trying to do is to find the descriptors of this normal distribution that will describe for us the duration of the whole project. We know that this distribution is going to be a normal distribution, so since it's a normal distribution, what we need to know is the mu value and the sigma value for the distribution, the mean and the standard deviation. And the mean, as you can see here, is depicted as the sum of the durations of the activities on the critical path. That's the point. So what you're doing in this example is that you take the mean values of the activities on the critical path, of the duration of the activities on the critical path. The activities on the critical path are A, B, D, and F, and you add them up. Please note that this formula is going to be valid when you do it on the critical path only when the dependencies between the activities on the critical path are finished to start. If this is not the case, then the mean value of the project overall would be the early start of the finishing node. But for now, keep in mind that you can do this addition and come up with a mu value of the project. So now we have one of the basic descriptors statistics of the normal distribution that describes the duration of the whole project, and that is mu. We know that the mean value is 18 weeks. What's the next one? The next one is to calculate the sigma for the whole project, so the standard deviation for the whole project. And this is a little bit more complicated, but still it's simple mathematics. So what you need to do is to square the standard deviations of the activities on the critical path, add them up, so square the activities, square the standard deviations of the activities on the critical path, add them up, and then take the square root of the sum. Let's see the example here. So the critical activities are A, B, D, and F. You can see you have calculated the sigma values for each one of these activities. You square the sigma value for each one of these activities, and then, so we are here, let me point it out. So that's the formula, okay? And then here you have the sigma for each activity squared, and this is for all the critical activities. That's the outcome for each one of the activities, and you have to take here the square root of the sum, which in this case is 2.85. And since we have completed that, now we have a normal distribution. So this normal distribution with a mu of 18 weeks and a sigma of 2.85 weeks describes the possible potential outcomes for the duration of the project. We are going to use this curve in order afterwards to do the calculations of the statistics. And we're gonna answer questions like, what is the probability of finishing in less than 19 weeks? These are very important questions that senior management is very keen on knowing. But this is going to happen in the next video.